Hi students, welcome to the Organic Chemistry Chem 322. Today we will be discussing the regioselectivity in the E2 elimination reactions. First of all, if you see that there are certain compounds which has available two beta carbons, like here, if you see this compound, it has two beta carbons available. So there is the possibility that the proton will be removed from either of the beta carbon, and there is the possibility of formation of different products. But if a substrate has two carbons in which a proton can be removed in an E2 reaction, when the two carbons are identical, like here in this case, we have two bromopropane, we have bromine here attached with this carbon, and then there are two methyl groups attached, and both the beta carbons are identical. The proton can be removed with equal ease from either one, and the product of this elimination reaction will be the same in either case. Here in this molecule, if the proton is removed from this one or this one, we will get propene molecule in either case. So there will be no effect on the regioselectivity of the compound, the resultant product. The same is the case here. If the proton is removed from this carbon, we will get this product. And if we get the proton from this carbon, we will again get the same propene as the elimination product. But this is not the case always. If the substrate has two structurally different beta carbons from which a proton can be removed, then two elimination products are formed. And this E2 reaction is regioselective because more of the constitution isomer is formed than the other one. Then here comes the question of regioselectivity, because one constitutional isomer will be abundant or in more percent product as compared to the other one. Here, like the case is, we have two bromobutane. Here are two beta carbons available. One is this one at one position, and the second one is at the third position, third carbon. These two are the beta carbons. If you have a base, methoxide, or any one strong base, so it can remove a carbon, a hydrogen, or a proton. It can abstract a proton from any of the beta carbon. Now, which product will be found more is here. The 2-butene, it has 80%. 80% will be the 2-butene, and 1-butene will be the 20%. So the carbon double bond has been found between the 2 and the 3 carbons, or the 3 beta hydrogen, or 3 beta hydrogen has been abstracted by the base, this one, and we get 2-butene in 80%. What will determine the orientation? In substrates which have alternative beta hydrogen available for removal, it is possible to obtain more than one alkene on elimination. Like in the previous slide, there was a case that more than one alkene, that was 2-butene and 1-butene, that was found. Now, how will we decide that which alkene is more likely to be produced? It's governed by rules that are Zaitsev rules and the Hofmann rule. So, when we apply these rules, we can forecast that which alkene will be abundant or in more quantity. Zaitsev rule. What the Zaitsev rule says. The more substituted alkene product is obtained when a proton is removed from the beta carbon that is bonded to the fused hydrogens. This is called Zaitsev rule. If a proton is removed, if there is availability of a proton to which there are lesser number of hydrogen attached, so that product will be more stable, or that will be in more quantity as compared to the other one. Or we can simplify this rule. The more substituted alkene will be the one found by removing a proton from the beta carbon that is bonded to 2 hydrogens, rather than the beta carbon that is bonded to 3 hydrogens. Here, beta hydrogen, 2 beta hydrogen, 3 beta hydrogen. We have 3 beta hydrogens. Here we have 2 beta hydrogens, 2 chloropentane. So, according to this rule, that is, the proton will be removed from the carbon, from that beta carbon, to which fewest number of hydrogens are attached. That is this one, because here are 2 beta hydrogens. Or, according to this simplified formation, that product will be found where is the more is the substitution. Here, it is di-substituted, 2-pentene, and it is mono-substituted, 1-pentene. So di-substituted pentene is 67%, and the mono-substituted pentene is 33%. So that means that product, that alkene will be favored which has more number of substitutions. This one, 2-pentene. The more is the alkene stable, that will be the major product in an E2 reaction. And Zaitsev rule is just a shortcut to determine which of the possible alkene product is more substituted alkene. The more substituted alkene is not, however, always the more stable alkene. When conjugation is possible, then the conjugated alkene is the more stable alkene, even though if it is not the more substituted one. The major product of each reaction will therefore be the conjugated alkene, because being more stable, it is more easily formed. Okay, the Zaitsev rule says that the more substituted alkene is more stable, but if there is a conjugation present, then the conjugated alkene is more stable one, and then that product will be in higher percentage as compared to the more substituted alkene, as the conjugation give more stability to the product. Here, if you see 4-chloro-5-methyl 1-hexene, there is the possibility that a proton can be removed from this carbon or proton can be removed from this carbon. Now, at this position here is more substitution, but here you can get more conjugation. Here you see, if the proton is removed from this carbon, we will get a double bond here between these two carbons, and we will get 5-methyl 1,3-hexadiene, and that is a conjugated product, and that will be the major product. On the other hand, if the proton is removed from this carbon, we will get 5-methyl 1,4-hexadiene, and this is the more substituted. The carbon having the double bond have the more substitution, but it is a minor product. Why? Because the conjugation gives more stability. Here is another case. 2-bromo 3-methyl 1-phenyl butane. Here, if you see, again there is two possibilities to have a double bond, or a proton is abstracted from this phenyl aryl hydrogen, or from this other carbon. So two products are formed, 3-methyl 1-phenyl butene. The double bond is conjugated with the benzene ring, and that's the major product. Here 3-methyl 1-phenyl 2-butene, the double bond is not conjugated with the benzene ring, though it is more substituted, so it is a minor product. Now we will come to the limitations of Zaitsev rule. Zaitsev rule cannot be used to predict the major product of the reaction mentioned on the previous slide because it doesn't take into account the fact that conjugated double bonds are more stable than the isolated double bonds. When there is the conjugation possible, so the Zaitsev rules cannot be applied. So if there is a double bond or a benzene ring in the alkyl halide, do not use Zaitsev rule to predict the major or most stable product of an elimination reaction, because the conjugation gives more stability as compared to the substitutions. In some elimination reaction, the less stable alkene is the major product. For example, if the base is an E2 reaction, and an E2 reaction is sterically bulky, and the approach to the alkyl halide is sterically hindered, the base will preferentially remove the most accessible hydrogen. If we use a bulky base, then it will be difficult for the base to approach the most substituted beta hydrogen, and it will remove the hydrogen which is easily accessible. Look into this example. 2-bromo 2-methyl butane. It has two beta hydrogens available, this one and this one. But here we have a very much bulky base, T-butyl oxide. Now, this can remove this beta hydrogen or this beta hydrogen. But due to the presence of these two substitutions on this, in the vicinity of this beta hydrogen, the approach of the base will be difficult as to this naked beta hydrogen, and we will get the 2-methyl 1-butene 72% more as compared to the 2-methyl 2-butene, though there is substitution, but while the base is quite bulky one and it cannot approach this proton here. So the 2-methyl 2-butene is lesser as compared to the 2-methyl 1-butene. Okay, when a sterically 100 alkyl halide undergo an E2 reaction with a variety of alkoxides ion, the percentage of the less substituted alkene increases as the size of the base increases. So, as the size of the base increases, the Zaitsev product will be decreases. If the alkyl halide is not sterically hindered and the base is only moderately hindered, the major product will still be the more stable product. If the base size is not so much bigger one, or the molecule is moderately hindered, like here 2-iodobutene, it's not so much hindered, moderately hindered. So in this case, the more stable one product or the Zaitsev product will be the major product, 2-butene, and the 1-butene will be only the minor product, 21%. Hofmann's rules. The alkene will predominate which has least alkyl substituent on the double bond carbon. That is, if you look into this molecule and if we have two beta hydrogen here, A and B, and the leaving group is Y. So there is possibility that this compound may be formed or this one may be formed. This one is more stable as compared to this one. But if Y is the bromine, so this less stable will be 19% and the more stable will be 81%. But if Y is an amine, bulky amine, then the Zaitsev product will be only 26% and the other product that is not a Zaitsev product will be 74%. Hofmann elimination is an elimination reaction of an amine where the least stable, least substituted alkene, the Hofmann product, is formed. This tendency, known as the Hofmann alkene synthesis rule, is in contrast to the usual elimination reaction where Zaitsev rule predicts the formation of the most stable alkene. This is the case of Hofmann elimination, and the product is in contrast to the more stable Zaitsev product. When an elimination reaction which can produce two or more alkene or alkyne products, the product containing the less highly substituted pi bond is major one. Here. This one will be the major product. And this is the mechanism of this reaction. That first the amine is, tertiary amine is converted to quaternary amine, and then it reacts with a strong base, the silver, and then the amine is removed and the proton is extracted from the less substituted carbon. The Hofmann elimination reaction is an elimination reaction of alkyl ammonium salts that forms the carbon-carbon double bond. It proceeds through a concerted E2 mechanism in contrast with the most elimination reaction that yields alkenes which follow the Zaitsev rule. The Hofmann elimination tends to provide the less substituted alkene, as we have seen on the previous slide. Here, exhaustive methylation by treatment of amine with the methyl iodide, and we get an alkyl ammonium salt. And then it is treated with a strong base, silver oxide, and we get two products. Zaitsev product, more substituted alkene. This is a minor one. And Hofmann product, this is less substituted alkene, and this is the major product. Thank you very much. Thanks.